Hi and welcome everyone to one more lecture of probability and statistics. Today we will learn how to calculate moment generating functions for different probability distributions. First we will calculate M.g.f moment generating function for binomial distribution. As we know, probability function for binomial distribution is bx parameters n, p equals to ncx p raised to power x and q raised to power n minus x. And we know M.g.f is denoted by mxt, and this equals to E expectation of e raised to power tx. As we know, this is a discrete probability distribution, so this will equal to summation over x equals to 0 to infinity etx times probability function for binomial distribution ncx p raised to power x q raised to power n minus x. Now if we will expand this again, so we will get summation x equal to 0 to infinity ncx p et common raised to power x. As we know, et raised to power x and p raised to power x, we can take this in one and we can write this whole raised to power x and q raised to power n minus x. If you will see this formula, this look like an expansion of a binomial. As we know, 1 plus x raised to power n. This look like nc naught x raised to power n plus nc1 x raised to power n minus 1. So we can write this as p et raised to power x pet plus q raised to power n. I will tell you why. Because if we will expand this, our first term will be nc naught pet raised to power 0 and q raised to power n plus nc1 pet raised to power 1 q raised to power n minus 1. Similarly, go on ncn pet raised to power n q raised to power 0, and before this will be term ncn minus 1 pet raised to power n minus 1 q raised to power 1. And if we will expand this, first we will put value of x equal to 0. First term will be nc naught pet, x is 0, this will be 0, q n minus x, n minus 0, that is n, plus second term, when we put x equals to 1, nc1 pet raised to power 1 q raised to power n minus 1. Don't you think these terms are going in a pattern like this? So that's why we can write this summation as this binomial. So that is our answer. This is moment generating function for binomial distribution. Now we will learn how to calculate mean and variance for a given mxt moment generating function of a distribution. Now we know mean equals to np and variance equals to npq for binomial distribution, and as we have calculated, our moment generating function for binomial distribution is PET plus Q raised to power n. Now mean equals to E of x, and that equals to first derivative of moment generating function, and then we will put value of t equals to 0. We can also write this as d by dx of mxt, and then we will put value of t equals to 0. Similarly, if we want to find out e of x square, then this will be equal to double derivative of moment generating function, and that value of t equals to 0. So this will be equal to d by d x square of moment generating function, where value of t will be put as 0. And we know variance equals to expectation of x square minus expectation of x square. So this will be m double dash 0 minus m dash 0 square. Now we will calculate first m dash 0 in the case of PET plus Q raised to power n, that is moment generating function for binomial distribution. So d by dx of PET plus Q raised to power n, t equals to 0. Now first derivative of PET plus Q raised to power n will be equal to n times PET plus Q raised to power n minus 1 multiplied with derivative of this PET plus Q. Now derivative of ET will be ET only, so this will be multiplied with PET plus derivative of Q. Derivative of Q will be equal to 0, so it will be just PE raised to power t. And now we have to put value of t equals to 0 in this. If we will put value of t 0 in this, ET will equal to 1. So this will be n times p, and value of q is 1 minus p. So this will be p plus 1 minus p raised to power n minus 1 times p, as e of t is 0. So this will be n, p to p cancel, 1 raised to power n minus 1, that will be 1, and that equals to np. Our m dash 0 is np, and our expectation of x mean equals to m dash 0. So this will be PQ, NP for binomial distribution using mxt moment generating function, and we already know that mean of a binomial distribution is NP. Similarly, we can calculate double derivative of m dash, putting value of t equal to 0. So this will be, our first derivative was, we have to again derivate our m dash t and then put value of t equals to 0. Our first derivative was n times PET plus q, n raised to power minus 1 into PET. So as we know, by chain rule, u into v this derivative will be u dash v plus uv dash. So this will be, first we will derivate this part. So this will be n times P E T plus Q raised to power n minus 2. Now this power was n minus 1, so this will be multiplied before here, and again this will be multiplied by our v. So this will be P E T. Now we will derivate PET. So we will get PET only, because derivative of e raised to power x is e raised to power x, and then multiplied with u. So this will be n PET plus q raised to power n minus 1. And now we will put value of t equals to 0 in this. So this is n into n minus 1 Pe raised to power t plus q whole raised to power n minus 1 n minus 2, and multiplied by PET plus PET times n PET plus q raised to power n minus 1. Now we will put value of t equals to 0. So as we know, E of t will be 1, E of t will be 1, E of t will be 1, E of t will be 1. Now this will be n into n minus 1, 1 raised to power n minus 2. So this will be 1. So this will be n times n minus 1 into P plus P n P plus 1 minus P, this will be equal to 1, 1 raised to power n minus 1, this will be equal to 1. So this is our value for m double dash 0. So now value for variance will be n time n, if we will solve this, so this will be n square P minus np plus np. So this will be cancel out. So value for m double dash 0 is this, and now value for m dash square. So this will be n square p square. So this is n square p minus n square p square, and we can write this as n square p minus n square p square. So this is our value for variance, and if we will solve this afterwards, we will get npq.